to all of you. So, today I am introducing Professor N.D. Haridas. Professor N.D. Haridas earned his PhD from University of California, Santa Barbara, and has conducted research and taught at prestigious institutions worldwide, including University of California, Los Angeles, the Max Planck Institute for Physics and MIT in Amsterdam, the universities of Utrecht and Amsterdam, and IIA in Japan. He has also worked in India at the Raman Research Institute, Institute of Mathematical Science, Indian Institute of Science, Chennai Mathematical Institute, and Tata Institute of Fundamental Research. Professor Haridas is a fellow of the National Academy of Sciences in India and has published over 600 peer-reviewed articles on his research areas, which include Lattice gauge theory, quantum field theory, gravitation and astrophysics, and foundations of quantum mechanics. He has extensive teaching experience at the undergraduate and graduate levels in both USA and India. He is the author of the book The Principles of Thermodynamics and the revised edition The Essentials of Thermodynamics. So it's a great honor to have Professor Haridas with us. So now I invite Professor Haridas to deliver the lecture on why quantum mechanics. I hope all of you will make use of it. And it's not going to be a presentation type of lecture, it's a blackboard lecture. Okay, so you can take down all the notes and also you can open the chat questions. Okay? Welcome.
Thank you. Thank you very much. This is going to be an informal lecture, so don't feel afraid to stop me, ask questions, okay? In fact, it will make me very happy if there are questions asked, okay? Because that will serve two purposes. It will help you clear your mind, and it will help me know how much you have understood or where you are, okay? And there is no such thing as a stupid question. Every question is meaningful. There is nothing called obvious. Okay? Everything needs understanding before you can say, oh, it's obvious. So keep that in mind. Now, I deliberately asked the department to arrange this talk on a blackboard. Okay? Because this is becoming like the extinct species, disappearing art. Okay? In fact, a few days ago on Facebook, I wrote the following, that blackboards are more important or matter more than black holes do. Now, why did I say this? I want to explain this a little bit. You know, this flooring makes a lot of noise. Huh? Black holes is a state of knowledge which people have got after decades of studying, thinking about it. But blackboards are a means to the knowledge. Okay? Not everybody can arrive at knowledge all by themselves. These days, nobody does. Even Albert Einstein didn't reach all his knowledge all by himself. So discussions are very important. And blackboards are a way of promoting the discussion. When there's a blackboard, you write something, other guy says something else, then you erase it and you write it, you erase it, you write it. So the message is the way we get to acquiring knowledge is more important than the knowledge itself. And in this lecture, not only am I going to use blackboards, I also want you to talk to me. Okay? So feel free, and you have the choice of Kannada, Hindi, English, Tamil also. And if you want to be very, very adventurous, you can try Danish, German, Dutch. So feel free. And I want to talk to you about quantum mechanics. Why do I want to do that? I will explain it in this talk. Usually when the lectures in quantum mechanics, it starts with some kind of a mantra, okay? And the usual mantras sound like wave particle duality, Schrodinger equation, Schrodinger cat, etc. Now I call them mantras because you hear and you don't understand anything. Most mantras they were never meant to be understood. Because if you understood, then you may question them. But if you don't understand, then everything is. But we don't want to do that. We want everybody to understand and question. Don't be disrespectful, but say anything you want. So I'm going to take quite a opposite path to this. I'm not going to straight away explain to you what quantum mechanics is, but I'll try to give you a flavor of why quantum mechanics is so important. Okay? So we'll do that first. And later, if there is time, I will explain to you what is quantum mechanics. So why quantum mechanics? To tell you, that's very, very important. Okay? What is quantum mechanics is to tell you what it is. So you may wonder, does it make sense? If I don't even know what quantum mechanics is, how will I understand your first talk on why quantum mechanics? So I presume that all of you have some familiarity of what it is. Even if you don't have any familiarity, don't worry about it. If this is called a pep talk usually, okay? Pep talk is when some cricket players or football players are about to go and do their thing. The coach comes and tells them how great they are and why they're important, blah, 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 blah. This is just to, encourage them. So this pep talk should inspire you to at least start thinking about quantum mechanics. So how will I do this? I will try to explain, without too much technical details, some important aspects that quantum mechanics has brought into our world. Now it's 1924. Exactly 100 years ago, quantum mechanics was born, in 1925. Almost simultaneously, Schrodinger and Heisenberg. They had very different approaches. They formulated laws of quantum mechanics, which have more or less remained unchanged in these 100 years. We have a much better understanding of them. We have very, very powerful mathematical ways of describing the quantum mechanical laws. But the essence of quantum mechanics, which they found, has remained more or less unchanged. And in these 100 years, it's not as if nobody challenged it, nobody questioned it, etc. Some of the brightest minds, including Albert Einstein, they challenged quantum mechanics at every opportunity they could get. So this subject has withstood very intense debate. These debates are not like what goes on in our parliament. Okay? There is no debate there. One side comes with a placard, the other side comes with cricket bats, and then, it's all mayhem. Which is unfortunate because our lives are determined by the laws that are adopted in the parliament, and these laws are very, very complex, and they need a lot of debate. Okay? So quantum mechanics was not like that. Science is usually not like that. So we have quantum mechanics 100 years later. Why was quantum mechanics invoked in the first place? There are historical reasons which I won't go into, but there were some things glaring in the face because the popular picture of the atom was that there is a nucleus which is positively charged, and there is an electron, one or more, which are negatively charged, and they are held together. Unfortunately, Maxwell's equations tell us in order for this electron to go around, it has to be accelerated. If it's not accelerated, it will just go in a straight line. But it's going in an orbit. And that acceleration is provided by the Coulomb force between the positively charged nucleus and the negatively charged electron. Now, Maxwell theory says that if a charge is accelerated, it radiates. That's how we get this light. That's how we get radio propagation, transmission, etc., which is good. Did you know that Mysore was one of the pioneers in radio? The first privately owned radio was started here. And those of you who are in the habit of walking, sometimes you can walk up to Chellavamba Park and the KRS Road, there is something called Vittal Vihar, where All India Radio, the precursor of All India Radio, started. Then it became All India Radio. Now, that is good. But for physics, there was a problem because if the electron radiates, it loses its energy. The orbit becomes tighter, acceleration becomes larger, it will radiate even more. It goes on and it's a runaway process. The electron loses all its energy and the atom collapses. There can be no stable form of matter. Now, this is very, very serious, right? We are all here. We are stable. We think we are stable. At least physically we are stable. And hopefully mentally also. But this atom had a problem. And that's why quantum mechanics was involved. And the final resolution, after a lot of false starts, was the formulation of quantum mechanics by Schrödinger and Heisenberg. And through the Schrödinger equation, you can look at the electron in the hydrogen atom, and you find that there is no continuum of orbits as in Kepler motion. There are discrete orbits, and one with the lowest energy, there the electron doesn't radiate at all. Beautiful. Higher levels, it keeps radiating, keeps coming down to the ground state. There it's. So it means that if you leave atoms for a very long time, they'll all settle down to the ground state. Stable. Okay. Now the laws of quantum mechanics, laws, LAWS, had tremendous repercussion on our understanding. To now understand chemistry. Without quantum mechanics, you couldn't understand chemistry. Because the chemists have a notion called valence, where there is one atom here, another atom there, and they talked about some electron being shared between atoms. Yeah. You have to give a mic, or you have to be the mic.
You mentioned Kepler, like continuous orbits and the planets with Kepler. What do you mean continuous orbits and planets?
Sorry?
Continuous orbits.
Yeah.
Mention about continuous orbits. Meaning as if it's, you referenced it to Kepler, right?
Yeah.
Meaning continuous orbits.
Continuous means that in Kepler's theory, you can the size of the orbit is not fixed. So if it loses a little bit of energy, it goes into another orbit which is close by. More energy, another orbit close by. So all the orbits are close to each other, continuous. But here, the orbits are discrete. Okay? That's what I meant. So now, chemists talk about valence. The electron being shared between two atoms. Now, if you go back to classical theory and use Coulomb's force between electron and positively charged nuclei, there is no stable orbit that can cover both the nuclei. Okay? It's not easy to prove this, but you can do it. So valence doesn't make sense in classical theory. Only quantum mechanics came and gave meaning to valence. Not only that, the atomic shells, how they're organized, directly matches with the periodic table of Mendeleev. All the properties of elements can be understood, and you can go more. The whole of material science and chemistry has been transformed by quantum mechanics. That in itself is a strong reason to know quantum mechanics. Okay? Magnetism. Magnets we all love, or at least I love magnets. You know, to understand magnetism, you need quantum mechanics. Classically, there is no theory of magnetism that we see, like in permanent magnets. Okay. So these are some, I can go on talking for days about what all quantum mechanics is brought. I don't want to do that. I just want to highlight some things. So chemistry, material science, magnetism, etc. So each of these studies today has become a major area of research, teaching, with tremendous industrial applications, tremendous applications to healthcare, etc. What I will do is highlight some applications of quantum mechanics that will cover not only the influence on basic sciences, our basic understanding of laws of nature, as well as applications. And we are right in the threshold of what is believed to be the birth of quantum technologies. One never thought that quantum mechanics will lead to technologies, okay? So that's where we are. We are going to see a whole lot of quantum technologies that will revolutionize computation, it will revolutionize security, I don't know. Okay? So this is my layout. So let me start with one of the most outstanding consequences of quantum mechanics. Oh, by the way, I forgot to tell you that every Blackboard presentation requires a few color chalks. It's okay. So first I want to talk about, everybody has heard of it, everybody has used it, what are called lasers. They're fantastic. Okay? The deeper you understand a laser, you'll just fall in love with that. You know, my cat loves these laser toys, and he goes crazy because I just point it on the wall and he tries to figure out where it is coming from, jumps, and tries to make his own theory, and we have a lot of fun, you know, with lasers. How many of you can tell me, this is an acronym. You know what acronym is? Acronym is, you know, like I dot N dot DIA is an acronym. Misleading acronym because most people don't pay attention to punctuation and then it looks like you're talking about the country itself. So what is this acronym for? Anybody? So this is also a lesson for Rahul Gandhi because after a while people forget what the acronym stands for. Okay, so there's no point in giving a name like India. This stands for light, of course, amplification by stimulated emission radiation. That's what it stands for. Okay? I'll explain to you what it means in a little while. And how does the laser tube work? You have a tube here filled with some lasing material. Take ruby, for example. There's someone that gives red light, and you can have green laser, blue laser, etc. And usually, thermodynamics tells the probability of realizing a state of energy E given by the Boltzmann factor. So if energy E is high, the probability is low. There are some pre-factors so that when the energy is very low, also the probability is low. There is a power of E here. So somewhere around energy of the order of kT, you get the maximum population. But you can invert this population by very special techniques. By inverting the population, you change this balance and you make lower energy states with higher probability than what statistical mechanics gives. So they're unstable because they would like to come down and be in conformity with Boltzmann law. So this ruby is not just ordinary ruby, it is a population inverted sample. Now clearly, The population inversion depends on the energy. So you do it for some particular transition in Ruby. And then you send us some small light signal of that particular frequency. Here comes the magic of quantum mechanics. If you take an atom in an excited state, it comes down on its own to the ground state and emits some light, we'll say photon. And that is what we mean by spontaneous emission. It does it on its own. Later we will see that it cannot do it entirely on its own. But now if there is one quantum of light of the same frequency, the probability of the atom to make this transition becomes larger. This is quantum mechanics. I won't write any formula. So, in the presence of this first light, these atoms, their probability of making a transition becomes larger, and you soon have two photons. In the presence of those two photons, the probability of transition becomes even more, and very quickly you will have lots of photons, all with the same frequency. So a particular frequency mode, the amplitude is enhanced. The intensity goes as the square of the amplitude, so you get very, very bright sources of light. This is laser. Okay? There are fantastic applications of laser, both destructive and constructive. Human nature that every innovation, somebody thinks of the nasty part of it and somebody thinks of the creative. Okay? Now we can use lasers to control behavior of atoms. We can use lasers to control chemical reactions, etc. So the possibility for science is almost unlimited. In medical applications today, we can make very precise surgery. These laser beams can be focused to a very small area, and if some part has to be removed, you just burn it with this laser. Earlier, it depended on the surgeon's skill and how many packs of whiskey the surgeon had before the operation, and such details, and how thick the fingers were. By the way, surgeons have very thick fingers, but they're very nimble. So, and then when they try to cut one part, even with the best training and intention, they would cut another part. And this is how disasters happened in the early days of surgery. But today with lasers, you can pinpoint and take care of only that. In fact, this has become so precise that you can make an operation on a fetus in a mother's stomach. You introduce the laser source through a pipe and control them from outside. And if the kid or fetus has something that has to be removed, it will be done. So you see that lasers are a real boon to humanity. But how did this idea of lasers come about? This is all after the story. It started with the Indian S.N. Bose Sachendranath Bose in 1924, before quantum mechanics was finally formulated. And at the time, as you have learned through books, blackbody radiation was a big challenge. That's how Planck invented his Planck's formula. Bose had a totally different approach to this. In 1905, Einstein had a theory for the photoelectric effect. What is photoelectric effect? You take a metallic surface, you shine some light on it, and you can produce electrons, you can produce a current. Okay? So this is the basis of all solar cells and so on. This was established long ago. But it was very hard to explain this on the basis of Maxwell theory. Einstein said, if somehow we assume that the light that is falling on it is made up of particle-like objects, then photoelectric effect, all aspects of it. See, in science it's very important that when you give an explanation, you should explain as many things as possible. You can't cook up a theory for every fact. This is what many people who are constantly claiming that they have sent Einstein to the boondocks or that quantum mechanics is wrong, etc. They don't understand. They pick up something and they have their peculiar theory. At one point there was a theory which said that you build a pyramid and you sleep inside and you become a genius. Okay? Or if you're a non-vegetarian, you can keep a piece of fish and that will not go bad. Because there are all kinds of theories. But even if they explain one, they'll not be able to explain everything. Here was Einstein's very simple idea. It was very simple because everybody understood how billiard balls, when they strike each other, what happens. Or when you play cricket or ping pong, what happens, when you give momentum to a ball, okay? He could explain everything. A whole lot of things about photoelectric effect. These were named photons by a chemist, Gilbert. He was a chemist. He gave the name photon, not Einstein. Now, the genius of Bose was to look at the blackbody problem a completely different way. And he said, if Einstein is right, and it's really made up of particles, I should be able to apply what Boltzmann did to get the laws of gases, and he applied it. Of course, these photons don't behave like, cricket balls and tennis balls or classical atoms. So Bose had to make certain guesswork, but it was very profound guesswork. And one of them was that the photon particles are such that in a state that is with some energy, etc., you can put any number of them into that. And that's what happens in the laser. Because when you choose a mode, you can put arbitrary number of photons into that mode. So you can enhance the intensity almost without limit. So it was Bohr's idea, which was improved upon by Einstein, which is the scientific basis for lasers. Neither Bose lived on, but Einstein didn't see the creation of lasers. Okay, so that's the science part of that. And later, it turned out that light is not an exception. Even electrons behave the same way, atoms behave the same way, and everything behaves the same way. And you can have an analog of lasers for atoms. You can condense atoms, any number of them, provided they're like helium-4 and not like helium-3. And this is called Bose-Einstein condensate. It's a new state of matter which quantum mechanics predicts, and it has been created, and a lot of interesting physics has come out of that. Oh, 40 already, and I'm still going very slow, but that was my idea. What are these photons? Soon after quantum mechanics was formulated, some people started asking, why should we apply the laws of quantum mechanics only to particles like electrons and photons? Why not to fields? Okay. What is an example of a field? Is the famous Maxwell's electromagnetic field. So each point of space at any given of time, there are 6 field quantities, and they are the Maxwell's equations. Very, very successful theory. In fact, one of the most successful theories of physics. So people said, why should these not be subjected to laws of quantum mechanics? Whenever somebody says why, you can always say why not. Okay? So if somebody says a temple should not be inaugurated till it is completed, you can ask why not. Okay? Both are fine. So you have to have a friendly debate. Very simple reason was found why electromagnetic field had to be quantized. Okay? And I'll give you this. If you take a charged particle with some position r and some momentum p, the electric field is given by some E r cube r vector from the origin. So let's say this is the origin, and P at r equal to 0. Then this is the electromagnetic field, and the magnetic field is given by, again, there's a V over 1 over C, P cross R over. One of the hallmarks of quantum mechanics is the things like position and momentum, which could be measured arbitrarily accurately in classical physics, could no longer be measured. If you measure position very accurately, you lost all information about momentum, etc. That is quantum mechanics. Now, if electric and magnetic fields could be measured perfectly, perfect precision, then that would not be like quantum mechanics, where both these are measured simultaneously. Then you see what happens. I can use the information in electric and magnetic fields to infer the position and momentum of the particle at the same time. But the particle obeys quantum mechanics. So you cannot know the position and momentum at the same time. So if you do not quantize the electromagnetic field, then there is a contradiction. Okay? So this is how it was argued that electromagnetic field should also be quantized. Okay. That's one reason. Another reason, when most people are taught quantum mechanics, this is never told. Let's see what quantum mechanics says about an atom. That there is an excited state here, and there is a ground state here, G. And the atom makes a transition from the excited state to a ground state and emits a photon. This is what is said. But if you only look at the atom, the excited state is what is called a stationary state. In fact, that's how you solve for it. You solve for stationary states. These are states of definite energy. Then, if it's a stationary state, then if you create an atom in an excited state, it will forever remain in the excited state because it's stationary. The probability of the state doesn't change with time. So there is no way an atom can actually decay. So what we are told about why we see these discrete levels overlooks explaining the most basic feature of quantum mechanics, that all these states are stationary states, and one stationary state cannot decay. So what's the resolution? The resolution is the atom is not there in the world by itself. There is an electromagnetic field which is quantized, and it starts with ground state, no photon, but the combined system of the atom in the electromagnetic field is no longer stationary. We can show this through mathematics. And therefore, the combined system of the atom in the excited state and the electromagnetic field in the ground state is not stationary, and its probability can change, and the probability to find it as the ground state and one photon is calculated. So this is the reason why the electromagnetic field has to be quantized. Now coming back to our laser, this is a shorthand notation for a quantum state that exists as a superposition of no photons, one photon, That's what the laser is, quantum mechanics. But now we've opened a new field. Earlier, we had geometrical optics, when the wavelength was very small. And when the wavelength was not very small, you had to use physical optics. Okay? But now, we have a type of optics which obeys quantum mechanics. And this is called quantum optics. It's one of the very beautiful, exciting areas where light that we see shows quantum mechanical properties, which can all be measured, and this plays a lot of role which I cannot go into. Now what happens? I have an electron described by quantum mechanics. I have an electromagnetic field described by quantum mechanics, and they are interacting in the sense that an electromagnetic field exerts a force on the electron, and the motion of the electron generates the electromagnet. So it is, both of them influence each other. The technical name is they interact. So the moral of the story is, just as for quantum mechanics, we had to use something like commutator, Heisenberg relation. For electric and magnetic fields, also you have to show that their commutator is not zero, they cannot be measured simultaneously. And now you build a mathematics of both electron fields and electromagnetic fields, and that is called quantum electrodynamics. QED. And generally what's happening is that fields are also quantized, and this is called quantum field theory. There is another quantum field theory called quantum chromodynamics. Which applies to the forces that bind protons and neutrons together in a nucleus. And today, the belief is that protons and neutrons are themselves made up of what are called quarks, okay? And they have a property called color, which is like electric charge, and this theory is called quantum chromodynamics. But the puzzle is, nobody has seen quarks. You take protons and bang them at very, very high energies, nobody sees quarks. Okay, for some reason, quarks cannot be seen, and this is called quark confinement. They are confined permanently inside the nucleus, and this theory called QCD, quantum chromodynamics, explains why quarks are confined. Okay? So this, I think it's almost 1 hour now. I will try to stop here so that we can have some discussion. So today's thing has partially shown you the importance of quantum mechanics for scientific parts like understanding QED, QCD, lasers, and also for technological applications like that of lasers and so on. Okay. Now I will continue in this spirit in another 5 days, and we will take this story forward. Now we can just have, if you have some questions, I'll be happy to answer. Yeah.
So, here you mentioned that quarks are always found inside the nucleus, and no matter how much you collide the particles, they never show up. And that is exactly what they're doing at CERN, right? That is exactly what they're trying to do at CERN, right?
Sir, Geneva.
In Geneva, they're trying to do that.
Do what?
Colliding the particles and trying to see
Yes,
that.
yes.
And so they.
What's the question?
The question is that they have been able to find different particles in different states, but is there any thought as to, like, is there any future where they can?
Can you repeat that question?
The future of CERN, why they are not able to find quarks?
Yeah.
What she has.
Future of any experimental facility, is you can only have some ideas, but you never know which way it goes. Okay? So they want to build facilities where particle collisions can be studied at very high energies, etc. And they give justifications because you have to ask for money. And if you just say, look, I'm doing it because I like it, it's a nice toy, nobody will give you money. So you promise, you say, I can find this, I can find that. But no scientist takes those things seriously because you never know what you get. But when you have a new facility, you're likely to find new things. Okay? But sun is not the best place to study quark confinement because this is what happens at lower energies. It so happens that if you take two electric charges, how strong the force is given by the fine structure constant. Okay? And that actually increases very slightly when you go to, decreases very slightly when you go to larger distance. But between quarks, what happens is, when you decrease the distance between them, the force becomes stronger and stronger and stronger. Okay? There is a decrease, I mean increase. When you increase the separation, the force becomes larger and larger and larger. That's why you cannot pull them apart, because the force required to pull them apart is so strong. This is what the theory QCD says. But there are precise details which you can study, and the various facilities. Some also studies it, but that is somewhat secondary. I'm sure you have something that you are very eager to ask, but you're not building up the courage to ask. Ask anything. Ask me if QCD gives you a better recipe to make Mysore Pak. It doesn't. You know, I want to tell you something. I went to America to study, to do my PhD. In America, the situation is completely different. No teacher ever asks students to ask questions. In fact, at some point, they have to tell them to hold on, okay? And they come munching on their hamburgers and feet on the chairs, and at one point even smoking, which was stopped later on. And they ask, and they're very loud. In America, the formula for success is the louder you speak, the more successful you will be. I don't subscribe to that, but you must open up and ask questions.
There was.
Yeah.
How can we explain? How can we explain what are the what mechanisms they are?
What is he saying?
How can we explain quantum mechanics to a lay person?
What?
Explaining quantum mechanics to a normal person.
To
a normal person. Okay.
Are you normal? Yes, it's a challenge, not just quantum mechanics, physics in general. Last month I gave a talk on why it's so hard to explain science. Okay, there's several reasons. One, language. Words that mean something to us mean something different to, let's say, non-technical people. Whether they're normal or not, I can't guarantee. That's one of the biggest drawbacks. When we say momentum, we have a very, very fine idea behind what it is. But in normal language, momentum can be used loosely to describe many different things. In Indian languages, there's hardly a distinction between force, strength, density, etc. The first problem. The second problem is mathematics. Okay? At some point, it becomes natural when you use the language of mathematics. But people, outside people, they freeze when they hear about mathematics. Okay? You will say in a hot country like ours, it's not a bad idea to freeze, but they freeze mentally. So there's a block about mathematics. All these things are due to the way physics and mathematics is taught. We don't explain why some kind of mathematics is used, can you use something else, etc. So our teachers have to change, our students have to change, our way of learning has to change, and we have to start looking at mathematics and ordinary language in very different ways. Okay? And this is not an easy problem. Now, there is a book on Salam, and it is called Trial of Abdul Salam. It's a nice novel, you should read it. This has been translated into Kannada, and it is called Abdul Salam and Vicharane. Now, trial and Vicharane is not the same. Vicharane is inquiry, and trial is something else. I don't know, what do you want to call it? Mukaddama or, something. So we have to come up with a very precise use of language and break down mathematics and remove the fear of mathematics, and then we'll be able to communicate quantum mechanics also to everybody. So 50 years, I'm not going to live for 50 years, But 50 years from now, you may have Bollywood songs singing about the beauty of quantum mechanics. Okay. Just imagine Deepika Padukone and Shah Rukh Khan, enacting the electron and proton in an atom. It's a serious problem. Think about it. Contribute. All of you should do that. Go back and look at the words that I used. Do you like it? I don't like it. Black holes. They call it Kapurandra. Now, what kind of a translation is that? In English itself, it was objectionable, but because some big honcho like John Wheeler introduced it, it got accepted. But for somebody who is hearing it for the first time, what mental image will be produced when they hear Kapurandra? Okay? So we have to find names that at least convey a little bit of what it's all about.
I have a question.
Yeah.
So you were talking about quantum chromodynamics.
Yeah.
And why did they give colors as a indicator to indicate quarks?
Sorry?
Why did they use the name word colors for quarks?
It's again, sometimes in the beginning when physicists think of new notions, they just give some heuristic names, okay? So there was a new feature about these objects, and it was not too bad to call it there in new colors, okay? But you shouldn't carry it too far. When something more was discovered, it was also called flavor. Then people started joking, they have a quantum theory of order and so on. So that's how it started. But once the nature of this new aspect became clear, the name just stuck on. That's all. Yeah.
As of now, the behavior of particles at quantum level is quite random, right? Actually random. The behavior of particles
Yeah.
at quantum level. So how do they use it in quantum computing to be able to calculate something when something is so random?
I was actually going to come to quantum computing at some part. Maybe I'll do it in the next lecture. Classical computing, your hardware is such that when the voltage in a transistor is above a certain value, you say it's 1. It's 0, below, it's call it 0. And the forces that are acting on it are just electrical force. Now, Feynman's idea was, why don't we directly use quantum systems? Can we use them as calculators? What is calculation? Calculation is you take some problem, codify it, and you have some algorithm, and that gives you the result, which is called a computation. Okay? Some people say even eating is a computation. That's very nice. At least we can motivate people to, understand computation. So now, coding part is like classical computation. But now, the operations that change the registers is quantum mechanics. So you must find analogs of 1 and 0 in the quantum world and use quantum operations on them to change the analog of 1 to 0, 0 to 1. But when you do that, because quantum mechanics is quantum mechanics, you get all kinds of new features which actually turn out to be beneficial for computers. This is how the quantum computing principle is. You try to think of gates exactly as in classical computing. Now, in classical computing, you can build your computer for your own calculation, and he builds it for his own calculation. It's perfectly possible, because you may be only interested in doing your problem very fast. and that is called special purpose computer. But such a thing you can't sell because people may want to use their computer to do a Google search on where biryani is cheapest, what the whole world says the worst biryani in Mysore. There are many places for that slot, okay? So you need something called a general purpose computer. You realize it through what are called logic gates. The logic gates is the same. The way they operate on 0 and 1 is the same. But any particular computation that you want is built out of these logic gates in a different way. Okay? So that's general purpose computing. Which means even if you don't know what a computer architecture is, you can still program. Otherwise, you have to do what is called assembly language programming, machine language programming. They are horrendous. So quantum computers also, you have to come up with general purpose quantum gates. And you can do that. You basically know the classical quantum and classical gates like AND, NAND, XOR, and so on. You can build corresponding quantum. That's the principle. But quantum systems are very fragile. Classical systems are also very fragile. You get a lot of errors. And so there is something called error correction, which is done at the hardware level itself. But if your computation lasts very, very long, I built a supercomputer in 2004 to do my lattice gauge theory computation. Those calculations would run 6 months at a time on a teraflop machine. 1 teraflop means 1,000 billion operations per second. And imagine that working for 6 months. The number of operations is huge. So a cosmic ray going through my cluster supercomputer could induce an error. So you have to overcome that. And quantum mechanics problem is much more serious because there is quantum mechanical systems, they're not isolated. They're always interacting with their environment, and the environment is also a quantum mechanical system, and it changes the behavior of your quantum qubits in unpredictable ways. And you have to correct for that. And this is the major challenge which is holding up quantum computation, that errors and error correction are very serious. So that's how quantum computers work. You basically use quantum laws for operations and use quantum states for registers. And in fact, that was going to be my punchline, that importance of quantum mechanics now is going into quantum technologies. It's a big thing.
Things at microscopic level are probabilistic in nature. But how is this real world certain?
This is a big question which nobody really understands. Okay? I mean, there is nothing probabilistic about me. Yes, there is. You know, before this lecture, they asked, do you want to have tea or coffee before lecture? And I mentally tossed a coin. And I said, okay, I'll have tea. Probability is there in our lives too, but it's of a very different type. And the probabilities in the real world can be controlled, etc. Quantum mechanics is not like that. But that probability aspect of quantum mechanics is for single systems. So if you do something on a single atom, you can't tell what the outcome is. But if you do it on a large number of atoms, it becomes predictable, okay? And this is called the ensemble interpretation of quantum mechanics. Individuals don't matter in quantum mechanics. Only ensembles do. Communists also tell you the same thing, that individuals don't matter, only the state matters, but we mean it in a very different way, okay? And in fact, I hope communists will not try to take undue advantage of quantum mechanics to drum support for their ideology. Therefore, one very crude way of understanding is that we are all made up of large numbers. But there is a mystery there. And that mystery is the mystery of atoms. That atoms are the ultimate description, and all atoms are identical. So you can talk about a large number of identical systems. And when you look at those large number of identical systems, then it almost behaves like classical physics. But this is not a proof. Nobody has succeeded in proving to any degree of satisfaction that a quantum mechanical system will eventually start beginning to look like classical physics. And while teaching quantum mechanics, all kinds of wrong examples are given. For example, it is said that if the number of particles is very large, then it becomes classical. That's not true. In quantum optics, I can create systems with large number of photons that will never behave like a classical electromagnet. Superconductivity is another example, which is macroscopic samples which require quantum mechanics to. So there are these edges which we don't understand. And this is one of the outstanding problems, but not many people want to work on it because it doesn't look good on your resume. You should do it when you've got a job, you've set up a family, one or more, and you're retired, and then it doesn't matter. It doesn't matter to you whether somebody hires me or not, and I can sit and think about such issues. But they're very deep. The classical quantum transition, we don't. Yeah. I'll come to you. Muhammad doesn't come to mountain. Mountain can go to Muhammad. Yeah, tell me.
What does condense?
Huh?
What does the word condense actually mean in a Bose-Einstein condensate? Is it like
Condense.
Is it like a water vapor becoming a drop of liquid?
Sorry?
Is it like water vapor condensing to become a drop of
Yes.
liquid?
Here, it's like the common usage. You know condensed milk, right? So what's the difference between condensed milk and ordinary milk? The milkiness is condensed in a smaller volume. Okay? So Bose-Einstein condensation means all the atoms are condensed into a state. Okay? Into a definite quantum state. So that's another example where even a macroscopic sample will not show classical behavior. You can make the number of atoms that have condensed as large as you want, and it is still not describable by classical physics. That's good. I'm glad there were some questions. And you see, it was, you didn't even have to sweat to ask a question. If you want, you can think over things, and next time we meet also we can talk freely. Okay. So
There are no questions. Then yeah.
watch out.
We'll stop it here.
Huh?
We'll stop it here.
Yeah. So thank you for your attention.
So yeah, we'll meet on 25th, that is Thursday, before Republic Day, and we will meet at the same time, same venue, same 4 o'clock on 25th. And I hope to see all of you on 25th also. And please do read up and come up with questions.
Bring your friends and family, your grandparents.
So whatever questions that comes to your mind by going through mathematics book, you can just put it down and come back with like a more question and answer on 25th. We'll conclude it here. Thank you. So I conclude it formally on behalf of the Department of Studies in Physics and Cosmos Mysuru. I would like to thank Professor Haridas for agreeing to give this lecture. First lecture, so we hope to do it more. I mean, we'll meet on 25th. Thank you.